Welcome back, class. Today we are going to begin our exploration of chemical equilibrium. So, in previous chapters, we've talked about how fast a reaction occurs, right? This is what we talk about when we talk about kinetics, right? The speed of a reaction. And now we're going to look at not how fast it happens, but how far the reaction proceeds. And this is determined by the thermodynamics of the reaction. Now, what do we mean by how far? Well, really we mean the extent or how much reactants are converted into products, right? Do we convert all the reactants into products? Do we convert some of it? So the idea is we'll use language like it's a product favored reaction or a reactant favored reaction. And so we can use this concept of equilibrium to describe the extent of the reaction. Now, the value, sort of the key value that we're going to work with equilibrium is something called the equilibrium constant. Now, you'll hear the term constant again, like we had when we dealt with kinetics, we had the rate constant. Right? And just like that, the equilibrium constant is a constant value, again, as long as we are at a given temperature. So, in a lot of equilibriums problems, just like kinetics problem, we'll use the temperature or we'll talk about the temperature even though we don't actually use it in the problem itself. Now, in terms of what the equilibrium constant means in terms of its value, well, generally speaking, the larger the equilibrium constant, so the bigger the number, the more product favored the reaction is, or farther the equilibrium lies toward the product side. So let's just take a model reaction here. And we'll think about when a reaction starts, let's just say we have only reactants there. And so at that point, the reactants are going to be consumed, they're going to react, and products are going to be made. And as this happens, the concentration of your reactants will drop, right, as they're used up, and the concentration of the products will start to increase. As the reactant concentration decreases, right, the forward reaction also decreases. Now, why might this happen? Well, if we remember back what has to happen for a reaction to occur, right? The molecules that are reacting have to actually interact with each other, collide, if you will. And if there are less and less of them, or lower and lower concentration of them, it's going to be less often that they collide, and so the rate of that reaction is going to decrease. Right? And we saw in the kinetics chapter that as concentration goes down, reaction rate goes down as well. Now, eventually, we'll build up enough products where the products can react to go backwards, to reform some of the reactants. And so we get what we call the reverse reaction happening. Now, of course, some of the assumptions that we're making here are that we're not allowing products to escape, say if they're gaseous products, right? We're either don't have gaseous products or we're not allowing those products to escape. So we have the concentration of the products are building up and we reach a high enough concentration they can react in the reverse direction. And as we build up more and more product, we start to increase the rate of this reverse direction. Now, any process that can proceed in both directions is termed a reversible reaction. Now, almost all reactions are reversible. Now, the thing is, on some reactions, the reverse reaction is so small, meaning either it proceeds to such a small extent or it's so slow that we consider the reactions to be one direction. And so we have reversible reactions. These are reactions that can proceed in both directions. Now, as that forward reaction starts to slow down, the reverse reaction is starting to build up as we build up products. Eventually, they meet, right? In other words, their rates meet. So, the forward reaction starts to slow down, the reverse reaction starts to speed up. At some point, those rates become equal, and that's when we achieve dynamic equilibrium, right? And this is the condition where the rate of the forward and the reverse reactions are equal. So when we say in terms of equilibrium, right, the in equilibrium is referring to the equal rates, right? And so that's the equal part of equilibrium. And so once a reaction reaches equilibrium, then the concentrations of all the chemicals, the products and reactants, will remain constant because product is being formed from the reactant at the same rate that the reactant is being reformed from the product. So as a product is made, it's reacting and going back to reactant. So everything stays the same. Now, we use the term dynamic when we talk about equilibrium to emphasize the fact that this reaction is constantly occurring. It's just we don't see any measurable change in the concentrations because things are proceeding in the opposite directions at the same rate. Now, I made a point to say equal rates is what we mean by equilibrium. It does not mean equal concentrations, and this is something that sometimes is confusing. When we reach equilibrium, it has no indication that we have the same amount of products and reactants. Almost never do we have that, right? Typically, a reaction will either be reactant or product favored, and so the key thing is what's equal is the rate that the reactions are occurring in both directions. So let's look at an example here. So let's take our reaction here between hydrogen, H2, and iodine, I2. And at the beginning of the process, we start out with just reactants. So in this scenario, we have 8 H2 and 8 I2, and we have no product. After 15, let's say we could just call this 15 minutes, right? We start to see product forming, right? And notice we now have 4 products, right? So 4 reactants and 4 products have reacted to give us, or reactants have reacted to give us 4 products. After 30 minutes, we reach a point where we have 8 products forming. So if we look here, we have 8 HI, we have 4 H2 and 4 I2 left. Now notice after 45, everything is still the same, right? We still have 8 HI and 4 of each of the reactants. Now what this is telling me that at this point, we've reached equilibrium. And so we can see here on the graph that the H2 concentrations are gradually declining as they react. The HI concentration is building up. And at some point, when we reach equilibrium, the concentrations reach some point, and then, importantly, they stay constant. Once equilibrium is reached, these concentrations won't change anymore. And so this is the idea. The reaction will proceed until it reaches equilibrium. Now, something I'll point out again, but just want to notice, you'll notice the use of this double-headed arrow. This is what we use when we're talking about equilibrium reactions, or reactions that are reversible and have meaningful amounts of both reactants and products. So as I said before, equilibrium concentrations, not equal concentrations. So when we talk about what the concentrations of our reactants and products at equilibrium, right? It's whatever they are, and they will not be equal, almost never. It's the rates that are equal, not concentrations. Now, all reactions are different, right? You'll have some reactions that reach equilibrium after almost all the reactant molecules are consumed, right? Those are very product-favored equilibrium. Other reactions reach equilibrium after only a very small percentage of the reactants are consumed. And these are what we consider reactant-favored equilibrium. So this is going to be individual for reaction, and the only way that we can know this is to do the experiments, right? We can't look at a reaction and predict this. We can only do the experiment and determine where the position of equilibrium is. What are the concentrations of equilibrium? They can only be determined experimentally. Now, as I mentioned before, the key value that we're going to use when we discuss equilibrium is called the equilibrium constant. And so, even though those concentrations are not equal, there is a relationship between them. And this relationship is expressed by what we know as the equilibrium constant. So we abbreviate the equilibrium constant with a capital K, importantly italicized, to differentiate it from the symbol for Kelvin, right, which is a capital K. So it's an italicized capital K, not to be confused with the rate constant, which is an italicized lowercase k. So we got a lot of k's here in these couple chapters, and so it's important to sort of keep those symbols straight. Now, how do we express the equilibrium constant? So it is the ratio at equilibrium, right, of the product concentrations raised to their stoichiometric coefficients over the reactant concentrations raised to their stoichiometric coefficients. And this relationship between the balanced chemical equation, right, we have those stoichiometric coefficients, and the equilibrium constant is called the law of mass action. Right? So this idea right here, where if we take our sample reaction, the equilibrium constant is the products, right? So we take the concentration, and notice the brackets here, that's indicating molarity, right? So our concentration units here are molarity. So it's the molarity of the products multiplied by each raised to whatever the stoichiometric coefficient is in the balanced reaction. So we have the molarity of C raised to C times the molarity of D raised to D divided by the reactants. A raised to A, B raised to B. And it's always products over reactants. Now, by convention, we leave the equilibrium constant unitless, right? These are all going to be molarities. Now, in reality, right, if these are different powers, then we might have some units of molarity, but by convention, the equilibrium constant is always given as a unitless value, right? Just as a number. So let's explore the equilibrium constant for a few reactions. So let's take our first reaction. So we got the reaction between 2 moles of N2O5 produces 4 moles of NO2 and 1 mole of O2. We can express the equilibrium constant simply by taking the concentration of NO2 raised to the 4th power, right? Concentration of O2 raised to the 1st power, typically left blank, divided by the concentration of N2O5 raised to the 2nd power, or squared. So again, it's always products over reactants raised to those coefficients. And that's how we're going to express the equilibrium constant for any reaction. Now to reiterate, the value, right? What does that value indicate? So again, if the equilibrium constant is much less than 1, so a tiny number, then the reverse reaction is favored, and we end up with what we consider a reactant favored equilibrium. So small equilibrium constant indicates reactant favored. A large equilibrium constant, so greater than 1, much greater than 1, means the forward reaction. And we're going to end up with a lot of product, and we're going to have a product favored reaction, right? So if we think about that mathematically, right, since it's always products over reactants, if we have a large amount of product concentration, right, our ratio is going to be greater than 1, right? It's bigger than reactants. So we can see how these things play out. If K is approximately 1, then that means we have a fairly equally favored, right? It proceeds about halfway, if you will, But typically we're going to lie in one of these two scenarios. So we can look at a sample of each one. So let's take this reaction where we have the reaction of hydrogen and bromine is equilibrium with 2 moles of HBr. In this case, we have a very large K, right? Times 10 to the 19. And this is telling me that we make a lot of product, right? The top of this ratio is going to be much bigger than the bottom of the ratio. And so that's going to result in a number much greater than 1. Take a different reaction, like N2 plus O2 goes to 2NO, and we see we get a very small K value to the negative 31st, which indicates that the values on the bottom, the values of the reactants, are going to be much larger than the concentrations of the products on the top, resulting in a very tiny number. Okay, so we want to understand how to work with the equilibrium constant and what those values mean.